Okay. So what I'll say regarding housekeeping is that we need to get, we'll get these graded and posted. Homework 8.5 is due today. I don't have a homework assignment for you today. I'm going to give you a homework assignment on Wednesday that's due on the Friday of dead week, and that is it. That is it for CE 312, other than the bonus assignment where I have you all upload proof of course eval and whatnot, but I don't have that loaded yet. Okay. Let's talk about the project, because the project is due on Friday, okay? So what I have here on the right is I have some hints for your submission and a checklist for your submission, because I know the project is coming up, so I'm starting to get a lot of questions about it. To credit, I'm actually getting a lot of different questions, like different students are having different issues, which is usually a good thing. That means everybody's sort of like, already in the details and just have specific issues about their projects, which is completely fine. As a general hint for everybody, I would suggest reviewing the recording for lecture 13, because that's the lecture where we went through the project as a whole, and it would probably serve as a nice refresher just, for what you're doing, especially if you don't know where to start. That would be a good thing. And then I also posted that video on VLOOKUP and data validation. It's not hyper necessary for the project, but I think that that VLOOKUP and data validation file will take half an hour's worth of iteration in Excel and turn it into a couple minutes worth of iteration in Excel. We'll make that go a lot faster. As for your checklist for your submission, so you're going to be uploading several files, okay? You're going to upload your Math 10 analysis file, and when you upload that file, what I want are the real loads and the final member choices. And if you do that, your answer in Excel should match your answer in Math 10. I did have one student who said, well, what if it's like 1,000 thought? That's probably fine, just like in terms of how Excel rounds versus how MATLAB rounds. But if it's appreciably off, something's wrong, okay? That means either something in your Excel sheet is being computed incorrectly, or maybe you think you have a W12 by 90 assigned here and it's actually not. So, but again, they should largely match. Computations and write-up. So again, for the computations, what I'm interested in is make sure that your members meet the stress limits, the truss meets the deflection limit, and that you computed the cost of the structure. And then your write-up, remember you need to do a reflection, basically suggesting if you had to go back into a time machine and go back in September, what would you do differently if you had to do the project again? Okay, and then finally, I do want a drawing of the truss on a PDF, 11 by 17. I don't care what software package that you use, but in the assignment, I have a checklist of what I want on that CAD drawing, and I have an example of what the CAD drawing should look like posted on Blackboard as well. Okay, sound good? Okay, everybody get the code? Everybody get the code? Okay. One thing I'll mention that we're going to be doing for the rest of the semester is discussing matrix analysis. I would ask that everybody bring their laptops on Wednesday. I'll show you something. Let me go to Blackboard. So here's Blackboard. I'm going to refresh the page. You should now see in Blackboard a new section in the lecture notes. So if I pull this up, this is a section on... to go into lecture notes, this is a section on matrix analysis, okay? And there's a lot going on in here, okay? So a couple things that are going on in here. I've got the lecture notes posted. I also have 2 procedure guides, which these procedure guides are going to make sense today. I've got one for bars and one for trusses. We're not going to do beams and frames together because this isn't really a matrix analysis course. We could teach a whole course on finite elements and matrix analysis. I just want to give you the overall picture of how these programs work. So we're just going to do bars and trusses. But I also have an Excel template, which we're going to use together on Wednesday in order to sort of finish out the example we're going to start today. So Wednesday, I want everybody to bring their laptops, okay? Sound good? All right, so everybody get the code? I don't think you got the code. All right, okay. Okay, so let's talk about matrix analysis, okay? And this is, so let me go through my goal with you for matrix analysis for the next 4 lectures. I took an entire course related to this in graduate school. Actually, scratch that. I took 2 classes related to this in graduate school. And even though I had 2 fully dedicated courses to this in graduate school, matrix analysis also popped up in a lot of other courses that I had, like elasticity and vibrations and whatnot. So this stuff shows up a lot in applicable engineering problems. And I imagine that if anybody here gets a job as a structural engineer and does structural design, you will be running matrix analyses at some point throughout your career. Like, you're just going to. So I would think it's my responsibility to at least ensure that you kind of understand what happens whenever you run one of these programs. I mean, everybody here is running MassCAN now for your project, and we've already had a homework assignment on it, but let's just think about what happens. You create this model, you pre-process, you create the geometry, the nodes, the elements, the boundary conditions, you apply the loads, and then you click this little button called solve. And it just magically gives you the answer for literally the entire problem, okay? And my goal is I want you to kind of understand what it's doing in the background. You're going to be, if you do this, as a practicing engineer, and you run into a problem when you model a structure, you're not going to have a Dr. Mike in the background say, oh, do this, do that. Like, it's going to kind of be your responsibility. And so I think at least having a rough idea of how the program works is beneficial. And so that's going to be my goal for the next few lectures. Okay? Now, to set the stage and to get everybody, on the same page, let's look at a basic mechanics problem. So I take a bar, I apply a load L, and I yank on it, or a bar with a bar that is of length L, and I apply a load F. Sorry. So if I apply a load F to a bar with a length L, it deflects or it deforms some amount delta. Okay. And for mechanics, we know that delta equals FL over EA, right? That's the amount of stretch that a bar gets. Because, I mean, how do I get that? I have sigma equals P over A. I have the strain as the change in length over the original length. And then stress and strain are related with Hooke's law if we assume linear elastic behavior. Now, what I can do is I can sort of rearrange this a little bit. Instead of writing it like this, what I'm going to do is flip and multiply. And the way I'm going to do that is I'm going to say, all right, EA, so if I have delta equals FL over EA, I'm going to rewrite that as EA over L delta is F. Or in other words, K delta is F, or is F. Okay? So this term EA over L, I'm going to use a specific term for, or a name for that. I'm going to call that the bar stiffness. Okay. So the term stiffness, it's very akin to a spring problem from physics. You probably remember that. You had some system that had a spring on it, and then the force in that spring was equal to Kx. Spring constant times however much it's stretched or squished and whatnot. Okay. Well, the reason I bring that up is that if we're looking at a truss, at a structure, I propose that instead of looking at it as this big complex system, I instead would like to break it down into its base components. And I propose that that truss is just a bunch of bars, or more specifically, an assemblage of bars. So I propose that instead of looking at a single spring constant and a single deflection and a single force, we can look at a spring matrix and a vector of displacements and a vector of forces, okay? And we can turn this basically into a matrix algebra problem, okay? This is how MassCAN, or really any matrix analysis-based software package works. I mean, the whole term MassCAN is matrix structural analysis. That's what it stands for, okay? But really any of the either simple programs or really nifty programs, whether it's STAD, whether it's RISA, SAP, whatever, they're all doing the same thing. They're all utilizing matrix methods to solve structures. Okay. The value of this is that we can define a single method, and by the way, everybody here has that method in front of you for a 1D bar element. We can apply this method to really any problem, and start to finish, we'll have the whole problem solved and every response we would need all at once. Okay? So how does it work? Okay, I showed you this flow chart before, but now I want you to rethink about it. Now we're going to dig into the details. Because like before, what would happen is, here's the model, we click a little button, Matt's hand does all this stuff in the background and gives us some answers. Well, now I want to understand all this. Okay? Now, you could find a number of different textbooks that give you different ways of organizing this. Like, I have it in 4 parts. Some textbooks might have it in 3. Some of them might have it in 7 parts, whatever. Like, at the end of the day, this is generally the same process, regardless of how you want to break it out. So, the first thing that we're going to do is look at the spring matrix, or the stiffness matrix. I probably won't use the term spring matrix anymore, but the idea is that you're going to write a stiffness matrix for each element in the system, and that you then assemble them into a global matrix for the whole structure. Okay? You'll understand how that works by the end of class today. You then assemble a load vector, right? And so if you go back to just sort of your basic problem right here, you start out by trying to get your K matrix, then you do your F vector, and then you say, okay, if I've got the K matrix, I've got the F vector, I can solve for my displacements with a little bit of matrix algebra, and then I take those displacements and I back substitute them into the rest of the system to get reactions, internal member forces, etc. And then when it's all said and done, you've got the displacement everywhere. You've got the force in every element. You've got the reaction everywhere, and it's all said and done. And now the only thing left to do is pick out the values that you're interested in, maybe generate any plots, what have you. And that's basically how matrix analysis works. Okay? Now, we are going to be using matrices, so we do need to have a little bit of a review of matrix algebra. I'm going to cover the stuff that I think is necessary to get through today's lecture today. Then on Wednesday, we'll talk about a little bit more. Everybody in here has probably done a little bit of matrix math at some point, whether it was in high school, maybe you did it in some of your math classes. I know we've done it in here, because remember when we did 2x2 joint solutions, when we had 2 diagonal members framing into a joint and we would solve 2 equations, 2 unknowns? Same idea, okay? But I want to be a little bit more global in some of the terminology that I use, and I want to make sure we're all on the same page. Okay. All right, so let's just go back to this. We've seen this before. So the idea is that we can write a simultaneous set of equations in matrix form, okay? And we did this, we did this a while back when we did joint analysis, and we had 2 equations and 2 unknowns, and we utilized their Casio FX115ES Plus or similar scientific calculator to solve them. Now, your scientific calculators are great for solving 2x2s. They're great for solving 3x3s. When you get to larger systems, you kind of do need to break out some software. And I will say, we could use MATLAB. We're not using MATLAB. We're going to do this in Excel. So, is that okay? I didn't hear anything. I thought, okay, so we'll use MATLAB? Now I'm getting some vocalization from the class. Okay, so today I'm going to go through some of the basic math, and then on Wednesday we're going to use Excel to do some of the computations. Okay, so let's get some terminology out of the way. I'm going to talk about matrices, and I'm going to talk about vectors. Okay, so what's going on here? So a matrix is just a table of numbers. That's it. Okay. So the terminology that we use is we say that it consists of the dimensions of a matrix are the number of rows by the number of columns. Okay, and so we'll typically say something like m rows or n columns, something like that. So like if we're talking about some random term in the matrix, it would be in the ith row and the jth column. So this A22, for example, is in row 2, column 2. Okay. So if I had some matrix, let's call this matrix C. So this is matrix C, a bunch of random numbers in there. If I wanted, so what are the dimensions of it? It has 3 rows, 5 columns, so it's a 3x5 matrix. And if I wanted to tell you what C24 is, row 2, column 4, that term is 7. Okay? And I'm just throwing this out here so that if you start seeing some of this notation a little bit later, it doesn't, like worry you too much. Okay. Now, in this topic, in structural analysis, we primarily only deal with two types of matrices. We deal with square matrices, and so a lot of times you won't even hear me even use the term square matrix, like just by the nature of what we're doing. If I say matrix, more often than not, it's implied that we're talking about a square matrix. Okay. The other term that will, or the other component that we'll use is a vector. Okay. So a vector is basically just going to be a matrix that has a single column. One of the things that might have been a little bit subtle here on the screen is that when we, if you open up a textbook and you look at the symbols that we use to define matrices, we'll often use bold letters, but bold letters are kind of hard to write by hand. But what I like to do is, because these are really all we're dealing with, what I kind of like to do is I'll say we've got matrices and vectors. I'll use curly brackets for vectors and square brackets for matrices. So if you see me using these terms, that's kind of my way of writing this in a bold fashion. I even kind of threw this here, there to sort of clarify what's going on. Does that make sense? So it's a simple way of us making sure we're kind of on the same page. Okay, so what can we do with matrices? Well, the first thing that we can do is we can add matrices. We can add and subtract them. We can multiply them by scalars. Now, in order to add two matrices together, they have to be of the same dimension, okay? And how do you do that? You basically just add element by element. So if I have this matrix A and this matrix B, if I want to add A and B, I'm adding these two matrices. All I do is just term by term, term by term, term by term. And so this will be -7, this will be 6, this will be 14, this will be 3, 7, 7, you know. That's going to be our matrix. Okay, that's how you add two matrices. How do you do scalar multiplication? Scalar multiplication is done on an element by element basis. So for example, if I have A and I wanted to do 3A, I would just say it's 3 times this, so it's 3 times every number in the matrix, and I get this. Okay. So maybe the flip side would be if I had a matrix like 2, 4, 6, 8. If I had a matrix like that, I could write that as 1, 2, 3, 4, and pull out a 2. If I'm factoring a 2 out, I'm factoring a 2 out of everything. Okay? Does that make sense? Okay. Okay. All right. What about multiplying matrices? Have y'all seen this before? Have y'all done this before at some point? Have y'all? Do they do this in one of the calculus classes? Like being able to multiply two matrices. Have y'all done this?
Maybe in Calc 1.
Calc 1.
That was like.
Did you do it in high school? Okay. All right. Okay. All right. So crash course in matrix algebra. Okay. So watch this up here. Okay. So in order to multiply two matrices, the matrices have to be dimensionally congruent. Okay. That is a mouthful. Okay. But what that basically means is that if you're multiplying matrix A times matrix B, this term and this term have to be the same dimension. Okay. Now I imagine many of you have not seen this. But I have a graphical way that I kind of like doing it. So first off, if you want to determine an individual term in the product, what you have to do is go along the row of this matrix and the column of this matrix and just sort of add them up, add up the products. Okay? I like to do it graphically like this. So I'm going to show you how it works here in a second. Okay? Now the big thing though is that this is probably the most important point that I want everybody to know, because to be honest, a lot of the matrix multiplication that we're going to do in here, we're just going to let Excel handle it for us. So I'm not like super worried that you need to be able to do matrix math by hand, but I do want you to know that matrix multiplication is not commutative. Okay? And what I mean by that is that in general, A times B does not equal B times A. Okay? You can't reverse the order of multiplication when it comes to matrices. You have to maintain the order. Now, There is one exception to that, and that is that when A and B are inverses of one another, which we'll talk about that here in a bit. So let me show you this. Okay, so watch this up here. So let's say I have matrix A and I have matrix B, and I want to multiply them. Okay, so this is what I like to do. Okay, I like to take matrix A, put it on the left, matrix B, put it up top. Okay, and notice how I've got these lines, like it's almost like a grid, like I did it on graph paper. The answer is going to go right here. Okay, and one of the nice things about doing it this way is that I know that I've got the same number of terms in these rows as I've got the same number of terms in these columns. So not only do I know I can do it, but I know the dimension of my final answer. So my final answer is going to have 3 rows and 2 columns. And how you do each term is this. Okay, so watch this. Let's take the first term, C11. Okay, so what I'm going to do is I'm going to do 4 times 2, which is 8, 3 times 1, which is 3, 8 and 3 gives you 11. Okay, for the next term, I'll do 4 times 5 is 20, 3 times 6 is 18, 20 and 18 give you 38. Okay, and then I'll just keep on going. Everybody see kind of the pattern there? I like it because it's visual. It's really easy to sort of see. And you can really easily get your final answer in the end. So that's your final answer. Okay. Again, we're going to let Excel do a lot of this math for us. But the big thing to keep in mind is you can't reverse the order. A times B does not equal B times A, except if they're inverses of one another. Okay. Probably the most important parameter of a square matrix is its invertibility. Okay. In other words, that if you have matrix A, that there is some partner matrix out there in the universe, B, such that A times B equals B times A, and that product is the identity matrix. Okay? So what is the identity matrix? The identity matrix is sort of the multiplicative version of the number 1 in matrices. So like the idea, let's say I have the number 4, okay? Its inverse, its multiplicative inverse is 1/4, because when I multiply these two, it doesn't matter what order I do it in, I get an answer of 1, okay? With matrices, there's really only one partner matrix with each square matrix if it's invertible, such that AB equals BA equals the inverse. And what does the identity matrix look like? It has 1s along the main diagonal, 0s everywhere else. Okay, so again, just think of the identity matrix as the number 1 when you're multiplying matrices. Can Microsoft Excel compute inverses? Yes. And in fact, the computation of an inverse of a matrix is like the whole topic of a field of math called linear algebra. So, okay. There are, and this is my linear algebra plug, there's often more efficient means than solving system of equations than just getting the inverse. For our purposes, this is going to be good enough for what we do in here. Okay. Everybody okay so far? That's enough math reviewed for today. We'll do more on Wednesday. Okay. So let's talk about matrix analysis. And what I'm going to do is I'm going to start my discussion for today and Wednesday with one-dimensional elements. Okay? And we're going to go through a procedure. We're going to go through an example problem. Hold on your arms. Now, what do I mean by one-dimensional elements? I want to start with elements that only translate left or right, okay? And just to be clear, mechanically, there's no difference between how a bar element behaves and a truss element behaves. The only difference is how we formulate the problem, because truss elements can move left or right and move up and down, okay? I'm going to restrict my motion to left and right. Is that a very practical problem in real-life engineering? No, okay? Is it small enough so that we can understand how this process works? Yes, okay? All right, so we're only going to consider systems that can displace longitudinally, okay? One thing we need to think about is for a given element, or a given component in a system, we need to start thinking in terms of what we're calling degrees of freedom. Okay? Degrees of freedom are how many total unknown nodal displacements there are. So I propose that each element in a system is going to have 2 degrees of freedom. So when I look at a given element, I propose that it's going to have 2 unique values that are going to define its displacement. How far this node goes and how far this node goes. So we call that delta 1 and call that delta 2. This is going to be a 2 degree of freedom node, okay? And I mention that because that's going to affect how we get our stiffness matrices and so on and so forth. Now, how are we going to do that? Well, let's first off recall some of the ground rules that we're using for matrix analysis, and you'll notice I blanketly copied a slide that I showed you a little while ago. Remember the terminology between joint and node and member and element, that those were going to be interchangeable. Remember that with units, everything needs to be consistent, so that's going to be important for what we do together. The sign convention, we need to refer to quantities consistently. So we're going to say that everything going to the right is positive, everything going upward is positive, counterclockwise is positive, tensile forces are positive, okay? You've already seen this before, right? I've shown you this, we showed you this when we did matrix analysis, or sorry, when we did mass scan. Okay, so with all that in mind, I want to take a look at a single bar element, and let's see if we can define what the element looks like, okay? So for a one-dimensional bar element, let's take a look at what I got here, and you'll see a lot of this is going to pop up that I have here on the board. So here's the element. So here I'm calling joint 1 and joint 2, or node 1 and node 2, okay? So here's the bar element. We're going to say that its E is constant, its area is constant, and that it also has some length L, okay? Now, keep in mind that forces and displacements to the right are positive. Remember what we said in matrix analysis, everything going to the right is positive? So I propose that there is an unknown force on this side of the element, there's an unknown force on this side of the element. I'm writing them both to the right because I'm initially assuming they're positive. If they come out negative, well then I get, a different answer, okay? I also have a displacement on this end and this end. I'm calling that displacement delta 1 and delta 2. I'm also showing that they're both going to the right. If they come out negative, it just means they're going in the opposite direction. Okay. Now we need to derive a stiffness matrix for this element. So what I'm interested in, here's what I'm interested in. All right, I want to define a stiffness matrix for this element. We'll call it KE. Stiffness matrix for the element, and I want to figure out what this is. I'm trying to figure out what that is, okay? And by the way, you already know what it is because it's right there on your handout, but we're going to see if we can figure this out, okay? We're going to see if we can figure this out together. Okay. Now, how are we going to figure that out? Well, we're going to use this right here, F equals K delta, which is EA over L times delta. We already figured that out. One thing I'll say is that if we were using a spring instead of EA over L, we would just use the spring constant, but so this will work for springs as well. Okay. All right. So before I start clicking through here the slides on the screen, I want to see if we can do this here on the board. Now, don't worry, everything I'm putting on the board is here on the slide as well, but I want to see if you all can walk me through what I have here on the slide. Okay, so I have here an undeformed element, okay, and now I'm going to do a deformed element. Now let me show you what I'm going to do, okay. I'm going to deform this element by taking this point and moving it over, taking this point and moving it over. But I'm not just translating it, I'm deforming it. So I'm going to do it in a little bit of an exaggerated fashion. So I'm going to take joint 1, move it about right there, take joint 2, and I'm going to move it all the way over there. Okay. All right, so just to put some dimension on this, I'm saying that this dimension right here is delta 1, and this dimension right here is delta 2. Does that make sense? Everybody okay on that? Okay, so all right. Does everybody in agreement with that, that delta 1 is less than delta 2? I mean, here's delta 1, big old delta 2, right? Now let me ask you a question. In order to do this, have I made the element longer than it originally was or shorter than it originally was? Like if I were to take a ruler and measure the length of the element here versus here, is it longer here or shorter here?
Longer.
It's longer, right? So how does a bar element get longer? What force do we apply to it?
Tension.
Tension. So I've applied a tensile force. Does that make sense? Okay. So in other words, I've applied that and that. I've yanked on it. Does that make sense? Okay. So let's see what happens. Okay. So we said that what? K delta is F, right? Okay. What is K? K is EA over L. What is delta? Delta is the total amount of elongation in the bar, right? Total amount of elongation. I propose that's going to be delta 2 minus delta 1. In other words, if this is 5 inches and this is 2 inches, the bar got longer by an amount of 3 inches. Is everybody okay with that? And that's going to equal F. So therefore, we have EA over L, and I'm going to rearrange this a little bit. So I'm going to say negative EA over L delta 1 plus EA over L delta 2 is F. Like, is everybody okay with that? Is everybody okay with my algebra right there? Does that make sense? All right. So, okay. Now let's see if we can relate this to this F1 and F2. So what is F1 and F2? Well, F2 is pretty easy. F2, so which way do I have F2 going over here? To the right, correct? So forces to the right are positive. Here's that going to the right, so this is plus F, which is negative EA over L delta 1 plus EA over L delta 2. But this one, here, F1 is positive if it's going to the right, but here it's going to the left. So this has got to be negative F. So this, I'm going to flip this sign and flip this sign. So I've got that. Does everybody see that? So I'm running out of room here on this board, so let's go over here. So I've got F1 is EA over L delta 1 minus EA over L delta 2, F2 minus EA over L delta 1 plus EA over L delta 2. If I wanted to write this in matrix form, these two equations, what would it look like? I'd have F1, F2 equals something here over here, delta 1, delta 2. How would I figure out what goes in here? The coefficients. So EA over L minus EA over L minus EA over L, EA over L. Does that make sense? So this, that's my stiffness matrix. And by the way, let's carry it forward. So, deform the bar, There's delta 1, delta 2. For the element to be in tension, delta 2's got to be bigger, right? So the stretch is delta 2 minus delta 1. Since the element's in tension, F1 acts to the left, so it's negative. F2 acts to the right, so it's positive. Therefore, chug it all out. Nice little pretty equation. Then do a little bit of algebra. By the way, hold on. One thing I will say, let me go ahead and say this. This is if the bar is in tension. Sort of keep your eye on these equations right here. If we were to say, okay, here's the bar in tension, but if we were to do it in compression, would we get the same answer? Well, we have some observed sign differences. This one would be bigger than this one. All right, so we'd have a different displacement there. We have this one positive and this one negative. But if we go through and carry out all of the arithmetic, we end up finding that we actually get the same answer as we did before. So these expressions work whether or not the element's in tension, whether or not the element's in compression. It actually works if the element doesn't have any load in it, because if delta 1 equals delta 2, then this will all come out to be a zero force member. So it's the same equations as before. So all we have to do is take this, do a little bit of expanding and rearranging, which is what I did here on the board, put it in this format, write it in matrix form. Boom, there's my stiffness matrix. Okay? I did that a little quick here on the screen, but I think between what I did on the screen and what I've got here on the board, this all kind of makes sense. Everybody okay with this? Okay. So let's go through the procedure start to finish for a matrix analysis. Okay? So now that you've got your handout, let's see if we can work through some of this. Okay? So part one is to assemble the K matrix for the structure. Okay? So the first thing we're going to have to do is write a K matrix for each element. We're going to have to assemble them into a K matrix for the whole structure. Okay? Now, assembly is something I'm going to show you here in a little bit. What it does is it corresponds to combining each of the terms in a likewise basis. So it's not the same thing as matrix addition. It's a little bit different, but I think you'll see what I mean here in a second. Once we have our K matrix for the structure, we assemble a force vector for the entire structure. This is really, really easy, because all you have to do is just look at the structure and get your force vector. That was really easy. The force vector is going to contain unknowns, though, at any degrees of freedom that are restrained. Those are the reactions. Okay? Don't worry, we'll do this together. Once you do that, solve for the displacements. This will be something that we probably do a little bit on Wednesday. What we do is we knock out the rows and columns associated with the boundary conditions. So we knock out the rows and columns of K and F and the columns of K as appropriate. And the reason why is when we have this big old system of equations, we knock out the rows that are associated with restrained degrees of freedom because we don't need those equations right at that step. And we can strike out the columns because when you do the matrix math, they end up getting multiplied by zeros anyway in your matrix multiplication. And so what we'll have is we'll have this big old K matrix, this big old F vector. We'll whittle it down into a smaller K matrix and a smaller F vector, which we call KR and FR. And they are reduced based on your boundary conditions. Don't worry, it's actually, this part's really easy and it's pretty visual as well. Solve the system. This is something that software packages can do all day, every day. It can be done on a scientific calculator as well. And then we will back calculate the results. This part is something we're going to do on Wednesday. But basically what you do is you write a displacement vector for each element, multiply by the stiffness matrix of each element to get the force vector in each element. And then we'll also do F equals K delta for the system as a whole to get the reactions. I'm going to blow through this part a little quickly because I want to get to our at least a little bit of our problem today. Ooh, we're running short on time. Actually, you know what? Here's what I think we're going to do. I don't want to rush this. I don't want to rush this. And we've got enough time today and tomorrow. I think what I'm going to do is, I was going to try and do a little bit of this today, but I don't want to rush it. The only thing I will do is talk a little bit about this example, and we'll just dive into it on Wednesday. Okay, so this is a bar element example we're going to do together, and I'm going to say a couple things about it. So first off, this structure is indeterminate, okay? And without an understanding of the relationship between forces and displacements, we cannot solve this structure, okay? Now that's not to say we have to use finite element analysis to do it, but we can't do it without understanding EA and L and EA and L, okay? So let me just say a few words about this before we leave today. So number one, notice how I've numbered each of the joints and I've numbered each of the elements, okay? The elements, so I'm trying to use some consistent symbols here. So I'm using circles for the nodes and I'm using square boxes for the elements, okay? And I mention that because I'm going to have something a little wild on your homework assignment, but if you just maintain that sign convention, it's pretty easy. Okay, a couple other things worth mentioning. Notice the units. This is in KSI, inches, and then I've got member lengths in feet, but I converted it to inches, converted it to inches, converted it to inches. The forces are in kips. Everything's in kips, everything's in inches. So when we start doing this problem, we're going to, like, ignore units. We're just going to blow through it, okay? Now, each of the elements have a node, a node, a node, a node, a node, a node. So each of the elements are going to have a K matrix that's 2 by 2. But the system as a whole has 1, 2, 3, 4. So the system as a whole is going to be 4 by 4. So one of the things we're going to try and do is figure out, so if we have the K matrix for the whole system, it's going to be 4 by 4. And we're going to try and figure out how to figure out these terms. And the way that we do that is we take the spring matrix for each element and we assemble it, okay? I don't want to get too far into what that means today because we don't have time to do it today, but on Wednesday we're going to do it start to finish. So here's what I want you to do. Wednesday, I want you to bring your laptops, and I want to show you something real quick. If you, like I said, if you go to Blackboard, you'll see under lecture notes, under matrix analysis, you will see this Microsoft Excel template. I'm going to show you what that looks like real quick. So here's what it looks like. And just so you're aware, so there's 2 tabs. So the first tab on the bottom is just going to be us learning how to do matrix math in Excel. So we'll start that really quickly. And so I've given you 2 matrices, and we're going to talk a little bit about how to add them, how to do transposes and multiplications and all that. Then we're going to get into our bar example. And I have this little spreadsheet set up that's got all the terms, it's all set up to be able to do the matrix assembly. It's set up to really do the whole problem. So I've got all the K matrices already figured out, but I basically got it set up to where we can knock this out pretty quickly. So on Wednesday, have this spreadsheet downloaded, have your laptop ready to go, and we'll get right to it. Does that sound good? We will see you on Wednesday.